Hello everyone, in today's video I'll show you how to design a Bluetooth controller to remotely control your Basys 3 board. We will be continuing from the previous project about the Servo controller, which means we will build a Bluetooth controller to remotely control the servo on our Basys 3 board. The Bluetooth module I'm using is called the HC05 and it communicates with the board via a UART interface. So today we will build a UART interface and use it to communicate with our Bluetooth module. This module has 6 pins, but today we will only connect 4 of them, TX, RS, ground, and the VCC. The VCC pin requires a power supply between 3.6 volt and 6 volt, so we will need an external power supply for it. This is our block diagram for today. Compared to the previous project, we have added a Bluetooth module here. We will send a degree information from our computer through Bluetooth to drive the servo. Once the Bluetooth module receives the degree information, it also sends it back through its transmitter to our computer. If you want to understand the servo controller, please watch my previous video. Here's the actual connection for today's project. So let's quickly open project number 6. Let's save it as project number 7, Bluetooth control. And to be honest, if you don't want to create a Bluetooth controller yourself, I guess you could simply use the built-in UART port in Vivado to communicate with the Bluetooth module. However, I want to create this driver myself, so I won't be doing that. I will create my own UART IP. First, we create a new XI peripheral IP to wrap our Bluetooth controller. Then copy the code from my website. For the UART interface, we will add 3 extra ports. One is a 10 MHz clock and a Bluetooth serial input bit for the receiver, and a Bluetooth serial output bit for the transmitter. We will use register 1 to store the data received from Bluetooth, so we need to comment out its current assignment first. Let's add our 2 files from the transmitter and receiver. And copy them from my website. For the connection here, we use register 0 for the transmitter. Bit 0 stores the transmitter valid signal. Bit 8 to 15 store the target transmitted data. For register 1, we store the data received from the receiver. For the TX bit and RX bit, they are connected to the serial ports of the Bluetooth module. Let's quickly take a look at the code. This module simply implements a UART receiver I won't go over the UART protocol right now, so if you are unfamiliar with it, I recommend reading through the protocol first. It's only a few pages and not too hard to understand. I've actually written detailed descriptions in the comments, so if anything is unclear, you can check out the comments in the files. Firstly, this module only supports one UART format with 1-bit start bit, 8-bit data bit, and 1-bit stop bit. Here's a 2-stage synchronizer. Since here is no shared clock between our system and the Bluetooth module, it's better to add a synchronizer to avoid metastability when sampling the receive bit from the module. Here's a simple state machine. When no data is being received, it stays in the idle state. If we detect a low-level signal for a while, meaning the start bit is detected, the state transitions to the simple state. We have a counter here to synchronize the baud rate. It counts to 1040, which represents the width of each bit for a 9600 baud rate. The detailed calculation is explained in the comments. Once the counter reaches 1040, we check if the current bit is a stop bit. If it is, we transition to the idle state. Otherwise, we continue sampling the next data bit. Here we determine whether the current received bit is a 1 or a 0 by continuously sampling it. If we sample enough 1 within the 1040 cycles from the current bit, we interpret it as a 1, otherwise it's a 0. Lastly, in the sequential part, we output the result once the entire 8-bit data has been determined. Here's the transmitter part. The basic concepts are similar to those of the receiver. The transmitter takes a transmitter valid signal from the XI register. Once the valid signal is asserted, it transitions to the send state to transmit data at a 9600 baud rate. Here, for different bit count values, we assign the output bit according to the target data we want to send from the XI register. I used 2 bits for the stop bit in this implementation. So I think that's all for today's RTL work. Let's synthesize it to check if anything's okay. Then let's merge all the changes we made. Click Repackage IP.